Hello and welcome to the What's New in RabbitMQ for vFabric 5.1 webinar. I'm Jerry Kuch, staff engineer from VMware working on the RabbitMQ project, and now let's jump in. So what we plan to cover in this webinar is to quickly review messaging AMQP, the RabbitMQ messaging system, and the Erlang substrate on which it depends. And this is an incremental update presentation. If you have no background in messaging, AMQP, or Rabbit, parts of this may seem unfamiliar or a little bit hard to follow, in which case refer to last year's webinar or the Spring Source or RabbitMQ website documentation. This is effectively an incremental update talking about the new features that are in RabbitMQ 2.8.1 as shipped in VMware's vFabric 5.1 suite. So we're going to break down the presentation into two sort of major thrusts. The first are new user-facing features that are present in the RabbitMQ server or broker, and then we'll talk about new features in the RabbitMQ client libraries. Then we'll move on to talk about some changes in internal RabbitMQ behavior that may affect the structure or operation of your messaging applications. And finally, we'll review some RabbitMQ supplementary resources both on the web, in print, and elsewhere that you can go to learn more about RabbitMQ and how to build effective messaging applications using it. So to begin with, we'll do a quick review. The AMQP protocol stands for Advanced Message Queuing Protocol. And in this context, advanced doesn't mean hard to use. It means featureful and flexible. AMQP is an open standard protocol like TCP and many others, which means you get wire-level interoperability supporting multiple implementations. Third-party analysis tools for the protocol are abundant and easy to write. For example, the popular packet sniffer Wireshark has dissectors that will pretty print AMQP frames and allow you to troubleshoot your AMQP applications or your connections or your systems. And another advantage of the openness of the protocol is that an open standard avoids vendor lock-in. The standard may outlive a given product or a given implementation or a given corporate parent or ownership, and all of these are advantages when you're building for the future. Moving on to specific advantages of the AMQP protocol. Compared to some other messaging systems where you may have more of a DBA type relationship where a special messaging system administrator with special tools and special privileges sets up the fabric upon which a messaging application depends, in AMQP all resources are dynamically created or destroyed by client applications as long as they're authorized to perform those operations. AMQP provides a simple conceptual model where three main types of entities that we'll review later do all of the handling of your messages. AMQP's openness, as mentioned earlier, spares you from vendor lock-in, and it supports a vigorous community both within and outside VMware. VMware itself is a member of the AMQP working group, which includes companies from many spaces, financials, networking gear makers, enterprise software providers, and so on. And these two things together, the flexibility and the openness of this protocol, give you many dividends. You get client libraries for pretty much any language or platform you might care to build your applications on, and you get many free tools and web resources. Next, we'll quickly compare AMQP to JMS, since in some sense they're in a complementary space, although they're not directly equivalent, as we'll see. First off, AMQP is actually a protocol telling you what messages look like at the wire level and what the command frames and their semantics are, whereas JMS is really an API that faces the application developer. AMQP is language agnostic. You can write your programs in Java, C# or whatever you prefer, whereas the J in JMS stands for Java, which means that you're Java or at the very least JVM bound. So you're going to be coding from Java or a JVM language. The AMQP working group is an open organization which has members from finance, system software, enterprise software, networking, and so on, whereas JMS is governed under the Java Enterprise Edition community process. In AMQP, as you mentioned earlier, your messaging resources can be client managed, whereas in JMS they're often managed more centrally and in a sort of more strict manner. AMQP is not yet as ubiquitous in the enterprise as JMS is, where on account of Java Enterprise Edition's adoption, JMS has sort of followed in. AMQP has, in some ways, greater flexibility than JMS. There's a focus on the routing of messages that JMS doesn't really have, since the latter really provides two basic producer patterns, queues and topics. AMQP also has some scalability advantages over JMS in that it handles large numbers of queues and exchanges, about which we'll say more later, very well, whereas JMS can be awkward when many destinations are involved. To give you an idea of this routing flexibility that we alluded to on the second to last line of that table, let's look at a couple trivial message fabrics that you might find in real applications. First, we'll look at an AMQP one. So in this message, we see there are producers who create and publish messages at the left side of the figure. The messages in AMQP are published into an entity called an exchange, which you can think of as a software switch or router that makes a decision based on the message's contents about where it should go. The exchange is then responsible for getting the messages that have been published by a producer into a queue, and then queues can be consumed from by one or more AMQP consumers. Here you see we have some consumers that are consuming from more than one queue, and we have some queues that have more than one consumer consuming from them. The JMS picture is a little bit more compressed in the sense that producers publish directly into queues and then consumers consume from the queues. You can have other topologies here where you might have exchanges that are routing to other exchanges, exchanges that are spreading messages over multiple queues that are bound to a single exchange, and so on. And these routing topologies can get relatively elaborate or be as simple as JMS allows, depending on the needs of your application. Finally, we'll stop and briefly survey Spring AMQP, since in a Spring Source webinar, it's likely that many of our developers are users of the Spring framework and surrounding tools. So with Spring AMQP, you get easier use of RabbitMQ in your enterprise Spring applications. The AMQP core abstractions are all provided in the Spring AMQP library, and you get specific RabbitMQ implementations of all of them. And those basically wrap the RabbitMQ Java client library in a more sort of Spring idiomatic way. The Spring AMQP library provides abstractions that wrap the things exposed by the Java client library to make them mesh better with your Spring application and take away some of the boilerplate and setup work that you'd otherwise have to do. For example, we wrap the RabbitMQ connection factory with some convenience classes in Spring AMQP that do automatic reconnection in the event of connection failure. There's a RabbitAdmin class provided in AMQP that allows you to build up the messaging fabric, your exchanges, queues, and bindings between them. There's a Rabbit template, which has convenience methods for sending and receiving messages. And then there's a convenient message listener container in which you can register plain old Java objects that asynchronously handle the delivery of messages coming into your apps. Also, there's Spring Integration, which provides many of the enterprise integration patterns from the book of the same name in sort of a canned form where you just add water and add them to your application. And for more information about that, you can go to the Spring Source website and look at the Spring AMQP pages. So before we wrap up with our survey of AMQP, we'll briefly say a little bit more about what those three major entities were that we talked about earlier and that we saw in the previous figure. So in AMQP, there's three main entities that handle the delivery and movement of your messages. There's exchanges, which, as we mentioned, are sort of like software switches or routers. A producer publishes a message into an exchange, and then depending on the type and configuration of the exchange and perhaps the properties of the message, it's decided by the broker where that message should ultimately end up. Queues are essentially FIFO containers that hold messages. The contents of a queue, namely the messages in the queue, can be held in RAM or they can be backed by disk, depending on what the user has asked of them or the conditions on the broker at the time. And there's various convenience options that can restrict who may use a given queue, automatically clean resources up when the last user of a queue leaves the disconnect from the broker, and so on. And finally, there are bindings. And a binding associates an exchange with a queue, thereby allowing messages to be delivered from the exchange into the queue. And whether a message is delivered over a binding to a given queue is dependent on the message type and the nature of the binding and the exchange type. So to get a sense of the lay of the land in the Rabbit world, at the very center of the universe is the RabbitMQ Broker, or the server. It's written in Erlang. Clients publish and consume messages into and out of it using the AMQP protocol. And in vFabric 5.1, we ship the version 2.8.1 of the broker. The current open source release is up to 2.8.4, and there's often a little bit of a skew between the vFabric release and the open source release, although in the future we expect that the distance between these things will be minimized, and support for the open source version is available from VMware as well if you have some reason to use that over the vFabric one. Around the RabbitMQ Broker are RabbitMQ clients, and there's a variety of these, as we mentioned, for different languages. The sort of principal ones in the enterprise world, at least, are the Java and C# clients. These are written by the RabbitMQ team at VMware itself. They provide good multi-threading support, taking advantage of the threading features of Java and C#, and these are distributed as part of the vFabric 1 product suite. There are also clients for Ruby, Python, and other scripting languages, and these are mostly community contributed. They're all open source. You can often write simpler, smaller, more expressive code in these scripting languages, but you may actually get, well, you're certain to get less absolute performance because of the interpreters those languages run in. You're likely to be restricted in what you can do with concurrency and asynchrony and so on, again, due to the limitations of those languages. And there are various options for writing clients in C if you're doing mobile or embedded or device or resource-limited applications. Finally, let's move on into looking at the actual new features that are exposed directly to the user in the new 2.8.1 version of RabbitMQ. First, we'll quickly review the history of Rabbit, and particularly the history of Rabbit in the VMware vFabric product suite. So vFabric 5.0, which was the first vFabric release, shipped RabbitMQ 2.4.1. The open source release of 2.4.1 was from April of 2011. vFabric 5.1 ships 2.8.1 of RabbitMQ, and that open source release of Rabbit was shipped in March of 2012. Going forward, VMware aims to release the vFabric suite twice yearly, and that should minimize the skew between the open source versions and the versions shipped officially in the vFabric suite. And so the new features in the new version of Rabbit and the new version of vFabric are spread among the broker itself, the plugins included to extend the broker's behavior, and the client libraries. So with that out of the way, let's move on and start looking at what's gone on in the broker since the previous presentation. So first off, the RabbitMQ control command, which is sort of the Swiss Army knife of operating and administering Rabbit, much as Apache control or Tomcat control are to those web servers, has got a few new enhancements. There's many enhancements in how Rabbit handles plugins. We now support high-performance Erlang, which may be of interest to certain types of applications. We've added a new AMQP extension called the Publisher Confirm. We've added a new and often requested feature called dead lettering. There's a new debugging tool called the Firehose Tracer, and the sort of keynote flagship feature of the new Rabbit release is an active-active high availability feature based on replicated queues that are replicated in the context of Rabbit clusters. The features vary widely in their impact and their complexity. Some are small cleanups and conveniences where others are major new features, and you'll see that reflected in where we allocate time in this presentation. We'll talk about, for example, active-active HA at much greater length than we will something like, the RabbitMQ control enhancements. So with that said, let's move on and go through this list from top to bottom. So RabbitMQ control has gained a handful of new commands. First off, there's a report command, which dumps an exhaustive report of the entire broker server status. And this is useful for support purposes if you're troubleshooting or debugging something. There's a RabbitMQ control environment command, which shows the settings and environment of the RabbitMQ application. And this is most handy when you're editing your RabbitMQ config files, attempting to change something, and you want to see what really is getting set in the broker. It's relatively easy to misedit a config file and either not change what you thought you changed or not change anything at all. And this is a good way to sort of see if what you intended and what was actually reflected in reality match up. And finally, what the RabbitMQ cluster status command exists, which breaks some of the functionality that used to be part of the status command out into its own separate area for more cleanly dealing with the case where you're clustering Rabbits, whether it's for HA or for scale. Plugin handling. In the past, you had to actually obtain and download your plugin EZ, which is the Erlang version of a Java jar file effectively, and you'd have to drop them in a special place and restart your broker and so on. There's now a new RabbitMQ plugins command that will list all of the plugins present on your system and allow you to selectively enable or disable them. And all of the factory provided plugins, i.e. those written by the RabbitMQ team itself, are now distributed as part of the broker package. So there's not a separate download anymore for plugins as there was in vFabric 5. If you look at this sample output from the RabbitMQ plugins command here, you'll see either capital E's or small e's beside the enabled plugins. A capital E denotes that you explicitly asked for this plugin to be enabled, whereas a lowercase e denotes that it was enabled because it was a dependency of something you did ask for. And so plugin management is much easier. If you do have old plugins, you install, if you have custom plugins or plugins you've written yourself, you install them the old way. You drop them in the right place, you restart the broker. In vFabric 5.1, VMware now supports more plugins, including the management plugin, which provides a web UI for administering Rabbit, as well as an HTTP API for monitoring tools or scripting or automation. The Shovel and Federation plugins are now officially supported, which allow you to connect RabbitMQ brokers or clusters across wide area networks at different sites. There's an LDAP authentication backend, which is often used in the enterprise for allowing single sign-on solutions that integrate with enterprise directories. There's a new SSL-based Rabbit auth mechanism, which implements sort of a SASL external mechanism where the identity of a connecting client is determined solely from the client cert that they present. And there's another text-based messaging plugin, messaging protocol that we have an adapter for called Stop. High-performance Erlang. High-performance Erlang is an Erlang feature that compiles Erlang modules to native code. The compilation is performed at server startup time. It's not just in time the way Java VMs do things. And in the way we've configured in Rabbit, only modules that are likely to benefit from native code compilation get compiled. The question of whether you should use high-performance Erlang or not depends on your application. If you enable it, you may get a 20 to 50% speed up on some workloads, but because you don't have just-in-time compiling and you have compilation happening at server startup, you may lose a minute or so of startup time on your broker node when you actually boot things up. So measure and experiment. If it looks like you're getting benefits that you need from high-performance Erlang and you can afford the startup time, then go ahead and use it. And otherwise, you can just start off by ignoring it and investigate it as performance tuning needs drive your attentions in that direction. With high-performance Erlang behind us, we now move on to the first big new feature of the new Rabbit release, and that's Publisher Confirms. So Publisher Confirms are a RabbitMQ extension to AMQP, and you can think of them as publisher acts. They're sort of the dual of what an AMQP act is. And so to make Publisher Confirms make sense in context, we'll briefly review what acts in AMQP mean. The AMQP act is effectively a transfer of responsibility from the broker to a consumer. A broker delivers a message to a consumer, and the consumer, upon taking possession of that message and doing whatever he wants to it, suppose he has to update a database record or activate some process in the real world, once the consumer has done that, he sends an act back to the broker. This tells the broker, I can forget about that message and not worry about having to redeliver it again. Whereas if you had a case where the broker had delivered the message to the consumer and the consumer had crashed after its receipt, but without taking action on the message, you'd want that message requeued for redelivery so that another healthier consumer could deal with it down the road. And so Publisher Confirms are sort of the producer side complement of this idea. Why would you want such a thing? Well, if you're publishing a message with the persistent flag set, which means please broker, save this message to disk so that if you crash, you can redeliver it when you wake up, such a message should survive a broker crashing and restarting. But if the broker crashes before it manages to persist that message to disk, well, there will be no record of that message having ever come in. The Publisher Confirm lets the producer know that the persistence happened successfully. So if you've seen the previous presentation and have worked with AMQP a little bit, you might know about AMQP transactions. And the question is, well, isn't this pretty similar to what you would do with AMQP transaction? And the answer is, in a sense, yes. The downside is with AMQP transactions is that they can be very slow, particularly if you're doing this sort of trivial envelope transaction where you begin a transaction, publish a single message, and then commit the transaction. Also, AMQP transactions are blocking. Publisher Confirms have the advantage of being implemented in a lighter weight way and being asynchronous. So the idea is that the publisher publishes messages, keeps track of those that haven't yet been confirmed, and sets up an asynchronous listener that upon the receipt of a Publisher Confirm from the broker, retires those messages so that the publisher no longer has to worry about republishing them into the broker. And so between this non-blocking behavior, this asynchronous consumption of the Publisher Confirms, and the sort of lighter weight internals, you may find Publisher Confirms could be up to 100 times faster than the sort of old-style trivial transaction of begin a transaction, publish a message, commit the transaction. The next new feature, dead lettering. So dead lettering has been an often requested RabbitMQ feature over the years. In the past, it's been possible to get most of what you want from dead lettering out of a RabbitMQ feature called alternate exchanges, although now we support it as sort of a first-class entity. So how does dead lettering work? When you declare a queue, you pass a custom extension argument specifying a dead letter exchange. The dead letter exchange argument identifies an exchange to which messages from that queue might be dead lettered if something goes wrong with their delivery. What are the conditions under which this dead lettering occurs? Well, if a consumer consumes a message and then rejects it, throwing it back to the broker, and says, I'm rejecting this message and I ask that you not re-queue it, then the message will be dead lettered. Also, there's a per queue time to live option on queues, which can cause messages that have been languishing undelivered in a queue for too long to be evaporated out of the queue, in which case the dead lettering process would move and publish them to the dead letter exchange. So how do you implement dead letter exchanges? Well, you use a normal exchange of the usual types. you can optionally replace the routing keys of the original message, and the dead-lettered messages may then undergo changes to the headers. The exchange name in the headers becomes that of the latest dead letter exchange to have processed the message. The routing key can be replaced if you ask for this, and the message is annotated with an array of information explaining why it wound up being dead-lettered. And this goes into something called the ExDeath Array. So the ExDeath Array gets one entry for each message each time the message was dead-lettered, and the entries are AMQP tables that contain the identity of the queue the message was dead-lettered out of, the reason it got dead-lettered. Did its TTL expire? Did it get rejected with requeue equals false by a consumer? When did it get dead-lettered? Where was it published to? What were the routing keys it was published with? And so on. The Firehose Tracer. This is a new debugging tool in RabbitMQ. This allows you to see every message published and every message delivered by the broker. You turn the feature on and off using the RabbitMQ control command, and then Firehose notifications get published to a special built-in exchange called RabbitMQ Trace. From this exchange, you can then bind queues to it, and then the messages, the Firehose notification messages, which are published into the exchange, will end up in the queues that you specified. A Firehose notification contains a routing key of the form publish exchange name or deliver queue name, the former being for messages entering the broker and the latter being for messages being delivered out of the broker into queues. The headers are unchanged from the original message, as is the body. So finishing with Firehose Tracer, now we spend at somewhat greater length some time on a careful discussion of the new high availability mirrored queues feature. So to begin talking about HA and mirrored queues, we should review RabbitMQ clustering. So first off, recall what a RabbitMQ cluster is. A RabbitMQ cluster is a logical grouping of one or several Erlang nodes, think of these as machines, each running RabbitMQ in its own Erlang virtual machine. Cluster nodes share amongst themselves users, virtual hosts, exchanges, and sort of queues, in the sense that they all know about the same queues, but any given queue only exists on one node in the normal case. Most of the state data is replicated in a cluster in an ACID style, and the usual exception to this is queues. Each RabbitMQ queue is identified with a single RabbitMQ Erlang process that manages that queue. Those processes only live within one Erlang VM on one machine, and they don't migrate about, with the exception of, in the case of mirror queues, which we'll talk about more in a second. So historically, why did you cluster? Well, the first reason you'd cluster would be for horizontal scalability. Because every queue is associated with a single Erlang process, essentially a given queue will never get more traffic through it than a single Erlang process can actually do the work of in the amount of CPU time that it's being scheduled for. So if you cluster, you could add additional machines, and thus additional Erlang VMs, and thus additional RabbitMQ nodes, and thus additional Erlang processes, and thus additional queues within them, and sort of make a wider, fatter broker with more queues. On the other hand, the throughput possible through any single straight line, any single queue, wouldn't get any higher. But by cleverly setting up your messaging topology using exchanges and bindings, as we saw and hinted at on some of the earlier slides, you can get around a lot of that. So why do you cluster today? Well, the horizontal scalability story still remains true, but also clustering is the basis for the new active-active high availability story, wherein the contents of a queue will be mirrored across more than one node, as opposed to just living on one node and being vulnerable to the failure of that node, as they were in the past. So in the past, prior to mirrored queues release, there was an older active-passive high availability story, which we'll review here a little bit. You can still use this solution, but remembering it allows you to contrast it against the new mirrored queue-based solution and figure out which one it is that you really would like to be using. So in the old style active-passive HA, persistent messages are written to disk on an active node would be recovered and redelivered if that node failed and a passive standby took over. But the setup and maintenance of this required a bit of work. You needed something like the pacemaker high availability stack to monitor your active, detect its failure, and then fail over the passive to take over for the now departed active. Many Linux distros include the pacemaker stack and most of the components you need, but you're still responsible for configuring themselves. Also, you'd need shared storage, preferably good shared storage, between the active and the passive node for these messages to be persisted to. You could use an open source system like DRDB, or you could buy a reliable, high-performance, fault-tolerant SAN from EMC or another vendor. But, you still had to acquire this stuff and set it up yourself, and it's one more piece of your infrastructure that you need in order to make this feature work. The new style active-active HA mirrors the contents of a queue across multiple nodes. So multiple nodes in a cluster can contain copies of the messages in a given queue. The set of mirrors is broken down into a master node, a master queue, and then slave mirrors of it. And if the master node fails, then one of the slaves is promoted to become the new master in a way that we'll talk about in a moment. So to review, active-passive, well, it's been available a long time. Your AMQP layer and your application can be basically unaware it's there. The downside is you have to maintain this hardware and software stack, both your monitoring solution and your shared storage, and you have to set it up and get it working in the first place. Passive nodes may take a while to step up, and you can have a period of sort of partial unavailability between the death of the active leader and the step up of a passive follower. With mirrored queues, you don't have these external moving parts. The downside is your application has to be a little bit more aware of what's going on in the cluster underneath. The queue replication has to be defined when you create the queue, and your application code has to be mindful of a couple little technicalities, which we'll get to in a moment. So mirrored queues use RabbitMQ clustering. When you create a queue, you ask for it to be mirrored across multiple nodes. One of these copies is the master, the others are slaves. The slaves apply operations occurring to the master in the same causal order they happened on the master, and all actions but publishes go only to the master. The master then broadcasts the effects of what's happened to it to its slaves. So clients really seem to be consuming out of the master, and understanding how the master and slave synchronize when things go up and down is understandable, is necessary to make sure that you don't lose messages unnecessarily. So, reviewing the promotion semantics. If the node that contains the master copy of the queue fails, then a slave gets promoted to master status. What if a slave fails? Well, the master remains the master. As far as the clients know they're consuming off the master and publishing into the master, they don't need to do anything. However, if the master fails, the situation is more complicated. First off, it's the oldest slave that gets promoted to be the new master. If there are no slaves that are fully caught up with the master, i.e. there's messages that exist only on the master but on no slaves, then those messages may be lost because the newly promoted slave won't have known about them. Further, when a slave is promoted, it considers the previous consumers to be disconnected. And this is to guard against another message loss case that could happen, which is that if the broker has delivered messages but consumers have not acted them, then we have to re-queue them for redelivery, because the consumer may have acted, and then the act could have been lost in flight from the client to the now failed master. Or, we could have lost the message during the sync up between the master and the slaves because the master crashed before the synchronization of the act to its slaves actually completed properly. So the bottom line is that the new master has to re-queue and redeliver any message for which it doesn't have proof that this was properly delivered and acknowledged. Similarly, there's a little work that the client has to do. We use a new extension to AMQP called consumer cancellation notification. And this tells the client to reconsume from the queue so that it will pick up the new master. This means the client won't continue throwing acts back at a failed master, and it can be prepared to receive messages that have been resent that it may have already seen, but where the act cycle didn't get completed due to failure on the broker. So, for looking into it in a little more detail, while the promoted slave becomes the master, no messages published to the mirrored queue are lost, because messages going to a mirrored queue automatically go to the master plus all the slaves, right? And that assumes that the message going into the mirrored queue set actually made it to all the slaves. So the next question is, how can you be sure a message actually got to all the places that it needed to in the mirror set? Well, again, we go back to the publisher confirm or transaction mechanisms that we talked about a bit earlier. Both publisher confirms and transactions are supported for mirrored queues, and the scope of their effect is all mirrored copies of a given queue. So the commit of a transaction only succeeds when the transaction has been successfully applied to all of the mirrors, master and all slaves in a mirror set, and a publisher confirm will only be sent back to the publisher after all mirrors have safely accepted the message. Thus, if you're publishing messages into the broker into a mirrored queue, then you want to make sure that they're all safely being taken responsibility for by the broker. Use one of these transfer responsibility mechanisms on the publisher side, either a publisher confirm or a transaction. And this guards against failures in the usual ways that we talked about earlier. So going on further into the synchronization behavior, a node can join a cluster at any time. And if you've defined a queue to have mirrors on multiple nodes and a new node gets added to the cluster, well, that new slave mirror will get created on the newly arrived node, and it starts empty, which is important to remember. There's no synchronization or catch-up protocol that causes the master that's ahead of a newly arrived and starting empty node to be caught up to the state of the master. And so from then on, as new messages get published into the mirror set, the slave mirror will get the new messages, but there may still be an overhang on the master because the master had messages that the new slave doesn't know about. However, as those messages are consumed out, recall they seem to get consumed out of the master. So eventually that overhang gets chewed down by consumption until such time as it catches up down in a sort of downwards direction with what's going into the slaves. And this is why we promote the eldest slave when a master fails, in the sense that the oldest slave is likely to have the smallest overhang between slave and master and be as close to caught up, and it will know as much of the history of the system as anything else surviving in the system does, and therefore what you might lose is smallest in that case. So the suggested best practice, if you're going to create mirrored queues, bring up all the nodes where you plan to have slaves exist prior to creating them. That way you don't have this, the master is now way ahead of a newly arrived slave problem. And again, publisher confirms and transactions will give you a clear, unambiguous indication at the producer side that your message safely got everywhere it was supposed to. And remember the key sort of rabbit mantra, which is true of most messaging systems, really all of them, which is that a happy rabbit is an empty rabbit. The system works best when queues are kept relatively short and rapidly draining and publishing and consuming roughly balanced. Because if you're publishing and consuming are roughly balancing, then you're not accidentally using your broke messaging system as a database, and the size of these overhangs between masters and slaves if you're using mirrored queues is automatically minimized. So, you know, this is one reason you monitor your broker. Because if you've got queues that are growing enormously and steadily over time, it probably suggests something has gone wrong in your application. There's an imbalance between production and consumption, something has slowed down, something has failed, or so on, and you want to know about that since it creates obvious risks. So continuing on with the behavior of mirrored queues, what are the consequences of nodes starting and stopping? Well, if you stop the master node for a mirrored queue, using RabbitMQ control or the management plugin or whatever, this looks like a failure, and the eldest slave gets promoted. So if you stop the next master, then the next oldest slave gets promoted, and so on. And if you keep doing this until there's only a master left and no slaves, well, if your queue is durable, then your messages, your persisted messages, will survive the restart of the node. And then as you restart the other nodes, they'll rejoin the mirrored queue. But remember, they come up assuming, you know, they come up in an empty state. They come up assuming that everything has been disconnected and that redeliveries might happen. And as a result of this, a rejoining slave can't know if its contents have diverged from the master that it's rejoining. So the rejoining slave will discard all of its durable local contents and start empty. And so this is just like the behavior we talked about before when a new node joins the cluster. So if there's messages you want to be highly resilient to failure, use publisher confirms or use transactions to make sure they got everywhere and got persisted. And if you're bringing nodes up or down for maintenance, think about what order you're doing it in. So to refresh some of the application-facing details, mirroring is specified, as I said before, at queue creation time. You can create a mirrored queue with no initial slaves, but remember the behavior. The new slaves are going to arrive empty, and they're only going to catch up to the master through sort of natural publishing consumption balancing. How do you declare them? Well, you use this extension HA policy where you can say either mirror my queue on every node in the cluster or mirror my queue on a set of nodes that I'm going to specify in the cluster. And then there's an optional argument in the second case that says, well, which nodes do I want the mirrors on? So here's a couple Java client examples. The first one uses the all policy, which causes the queue, my queue, that's being declared in the third line of that first example to be declared on all of the nodes in the cluster. And in the second one, you see we've created this policy parameters array on line 3 of the second example, where we've said node 1, node 2, and node 4, presumably in a cluster with at least 4 nodes, are all going to get replicas of that queue. So you specify either all the nodes or a specific subset of named nodes. It's not a thing where you specify a replication factor like I want 3 mirrors of it. You say, if you want 3, you say, well, I want it on this node, and then this other third node. Performance expectations. The safety you get from mirrored queues isn't free. Making sure that all of the mirrored copies of a queue get a given message requires messages to be passed within the broker, within the cluster, namely the message itself, plus some coordination messages to implement this sort of reliable atomic broadcast of the message to the mirror set. And so you should expect a performance hit of anywhere from 2x to 10x. But on the other hand, you should only use this for parts of your workloads where it matters. And in most messaging applications, there's different classes of messages that have different priorities and different importances that denote whether you can afford to lose some, or what their redelivery or what the guarantees you need to pay for on them are. Publisher confirms and transactions also aren't free. So identify the messages that really merit the cost such guarantees incur. Spread your mirrors about the cluster prudently. If you have some reason to believe certain nodes in your cluster will fail separately, i.e. they're on different power supplies or different switches or whatever, maybe put them there separately so that at least you've got mirrors in this thing that aren't going to go out with the same power failure. And then throughout deployment, measure, monitor, and check your assumptions. So to summarize on HA with mirror queues, it's a new feature. As we've seen in this sort of whirlwind tour, it can have complex behavior, and under this relatively complex behavior is a pretty sophisticated implementation. So to use the feature in practice, you want to read up on it in advance and develop as good a mental model of it as you possibly can so that you can see whether what you're observing actually matches realistic expectations of how the feature should work. And so you can read the HA docs on the RabbitMQ website, or you can look at the RabbitMQ in action book from Manning, which we have a reference to at the end, and study up on it there. And so keep your eyes open as you work with it. It's a sophisticated feature. The semantics are not always entirely obvious, and you'll want to have a good mental model that you can match your expectations against. And that brings us to the end of HA and mirrored queues. So other miscellaneous broker improvements. The management plugin now collects statistics more efficiently. It handles large-scale messaging fabrics better than it did before, and we have greater availability of the statistics database used by the management plugin, where we can automatically fail it over between nodes. There's convenience warnings of various gotchas, inaccessible virtual hosts that have no users that can't reach virtual hosts. So you'll get visual warnings in the UI of sort of these useless types of scenarios that you can accidentally create. And we have a new notion of access control to the management plugin, both the web UI and the API, where you can tag a user with multiple strictly nested levels of authority. So you can have either no access to the management plugin, you can have a management level of access, which allows a given user only to look at their channels, connections, queues, exchanges, bindings, statistics, and so on. Beyond that, there's a monitoring thing, which you can see various other attributes of the broker, but you can't actually modify them. So if you were writing a monitoring plugin for a logging system or a monitoring system, you'd probably give the user that it runs as this permission so that it could look around the broker but not destructively modify things. And then at the top of this hierarchy is an administrator privilege, which allows destructive operations like the creation and deletion of hosts, users, permissions, the closing of other users' connections, and so on. So the levels strictly include one another, so a given user need only be tagged with one, but this gives you more flexibility over the old all-or-nothing model that the management features had. There's a few new visual niceties in the UI. You can see dynamic rate of change of queue lengths in the management API. You can now publish messages conveniently from the management UI for testing purposes, and the management UI is now extensible by plugins, so you can add new features that have their own management UI that meshes with the existing stuff. Finally, while we're mentioning plugins, there's a few new ones shipped with the broker. There's now a visualizer plugin, which will show you a nice graphical representation of your messaging fabric. You'll see your exchanges, you'll see your queues, you'll see the bindings between them. And that can be really handy for troubleshooting your messaging fabric and figuring out whether it looks the way you want it to. And there's a new plugin called Federation. And so the purpose of Federation is to provide scalable pub/sub messaging across WANs. So you get a new Federation exchange type, which has behind it a backing exchange of one of the regular types. And then a federated exchange on a broker is linked over the WAN to an upstream exchange in another broker. And then messages published to the upstream exchanges are copied downstream to the Federation exchange as if they'd gone directly to it. In the figure you see there's a pair of upstream exchanges here on the left, and then there's a link through which messages published into these left two exchanges would be passed down over these links, which could be across the public internet, into the federated exchange downstream. And so the Federation plugin is sort of, in some ways, a generalization of the Shovel plugin that was available in earlier versions of Rabbit. Internal behaviors. A few internal behaviors have changed in ways that might change your application's behavior, often for the better. So first off, the ordering when messages get requeued has changed. Recall before, if you rejected or nacked or crashed after consuming a message, it would go thrown back in the queue, and it would get thrown to the back of the queue. Now when a message is requeued, its publication order relative to the other messages in the queues is preserved. This is a more natural behavior in many people's thinking than what Rabbit used to do. If your application worked well with the old, it was written to work well with the old semantics, it should work fine here, since in some sense this is a stronger condition. But it's worth knowing that the behavior will look different. There's a new internal flow control mechanism designed to control broker memory use and make performance more predictable, where the various components within Rabbit that might push messages amongst one another have a sort of debit-credit scheme enforced between them that keeps things from getting too far out of balance. It's worth knowing this is there. It doesn't require any user intervention to enable or configure. And finally, there's a disk space-based flow control, similar to our old memory-based flow control, where the broker will protect itself against low disk space conditions by blocking publishers. So as we approach the end here, we'll go look at some of the things that have changed in the client libraries. There's a new AMQP URI scheme, which has all the connection info in one URI. So this may be more concise than using the various getters and setters on the config objects in the previous APIs. The official clients now support publisher confirms. The thread safety in the Java client has improved. Channel operations can now be called from consumer methods, and consumer callback worker threads can be user supplied in a more sort of free-form way than they used to be. It used to be you'd want to actually restrict these objects for use on a single thread and avoid doing things within them. But again, if you wrote code in an synchronized defensive way in the old model, it'll still work with the new one because the new semantics in some sense are stronger and stricter than the old ones. Timeout options have been added in various places, so you can time out waiting for confirms. The RPC over AMQP client has timeouts, and we have a new builder API, sort of a fluent builder style, where you create a builder object for your various AMQP objects, set the properties on the builder object, and then have it emit one of them at the end by calling a build method. This can maybe be a little bit boilerplatey and a little bit less tedious to write and a little easier to read than some of the older APIs were. The .NET client has undergone some documentation improvements, and it's also picked up all of the analogous changes that the Java client has for supporting these new broker features. And so with that, we're done with the core content of the presentation, and we'll round up with some resources. So to learn more about Rabbit, the first place to look is the RabbitMQ.com website. Be mindful that the vFabric editions may have occasional slight differences from the open source releases, in which case you'll want to go to the vFabric Info Center at VMware.com. There's a new book just in print from Manning Publications called RabbitMQ in Action. And if you're looking at evaluating Rabbit or building applications on Rabbit or administering or operating Rabbit, this is probably the single best one-stop shopping source of information for Rabbit. The RabbitMQ website has lots of documentation, but the downside is there's lots of it there. It's not always clear when you first land on the site what order you need to learn things in. The sort of pedagogical structure of the Rabbit book is very good, and if you work through the Rabbit book or keep it at hand as a reference, all other Rabbit documentation becomes easier to work with. And then finally, there's a RabbitMQ Discuss mailing list that the RabbitMQ team itself frequents. And you can get to it by going to lists.rabbitmq.com. And if you're interested in following discussions on Rabbit features, development, best practices, and so on, this is a good place to monitor. If you want to learn more about the underlying Erlang that Rabbit runs on top of, which might be helpful for certain administrative tasks, although you certainly don't need to be able to program Erlang to run Rabbit, there's 3 good books here. The middle one is particularly strong on the OTP libraries, the standard libraries for Erlang that Rabbit is built using. And there are screencasts from the Pragmatic Programmer that take you through building a chat application of sorts using Erlang. And finally, there's a new online book called Learn You Some Erlang for Great Good, which is a fairly popular and decently readable source. So with that, we'll wrap up the presentation, and thanks for your attention.